It guided the entire Cold War in order to make enough nukes to make the drive.
All right. Well, I did finish up, polishing the proof that we talked about last time. So in case, some of you have tried to look back into this slide, I actually finished the whole proof. Okay. So instead of saying without proving the following is true, I changed it to say let's prove this by induction. So this is all done, and there's nothing new. It's just the formatting looks a little nicer compared to last time. But otherwise, it's the same as the proof that we talked about last time. So are there any questions about this particular proof, especially the induction step itself, which is, scroll, like here. It's basically exactly the same thing that we did last time. It's just that now I can actually display it as a sigma and stuff like that. No questions? So this is okay? It's all good? Okay, all right. So with this out of the way, we can now continue to talk about experiments more on experiments where ordering is not important, okay? Because the whole thing between a combination and a permutation is in permutations, the ordering is important, it is significant. So the tuple 1, 2, and 3 is considered distinct or different from the tuple 3, 2, and 1. Is that okay? So when sometimes ordering is not important. So I use an example here is when you buy a lotto ticket, okay, ordering of the numbers are not important, okay? In other words, the order of the numbers appearing on the lotto ticket has nothing to do with the order of picking the numbers out of the cage of balls, when they do actually pick the numbers. Does that make any sense? So how do we deal with, the cases where ordering is not important? So there are two ways to look at this. We can consider the odds of winning the jackpot of a draw, 3 from 6 mini lotto game. So this is basically a mini lotto game, but it makes it easier for us to visualize. Is I'm drawing only 3 numbers out of 6, and the numbers are just 1, 2, 3, 4, 5, 6. The outcomes of an experiment, in this case, to draw 3 balls out of 6, is using the old notation, the notation that we talked about last time, is omega, and then 1, 2, 3, 4, 5, 6 as the set of options available to the first choice, and we only have to choose 3 out of it. So this omega is going back to the definition of omega that we talked about in the previous class, which is basically just a way to generate all the possible permutations of choosing 6 out of 3. I mean, the other way around, choosing 3 out of 6 in this case. Okay, but it will give you all the permutations, not combinations, just permutations. So this is ordered. So now we'll go ahead and also say that we have a set of winning numbers. The set of winning numbers, in this case, W, is going to be a subset of the set where you choose all the numbers from. In other words, you choose 3 numbers and say, let's just say that 1, 2, 3 are the winning numbers, okay? So W is a set of 1, 2, and 3 as a set, not as a 3 tuple, but as a set. So in this case, W, or the cardinality of W, is going to be 3 because there are exactly 3 winning numbers. So now we run a sub-experiment. In other words, now we look at the actual winning numbers, 1, 2, and 3. And then we ask the question, how many ways can we arrange these 3 winning numbers? In other words, when we are considering how these numbers are picked out of the cage to begin with, how many ways can we pick out 1, 2, and 3? In what order, okay? But we already know the answer to that question because, once again, it is just the omega problem, because in this case, omega W, which has all the winning numbers, 3, will give us all the permutations of how we can choose those 3 winning numbers out of the cage. Is that okay? So the chances of winning the jackpot is now just the ratio of omega W3 as numerator divided by omega 1, 2, 3, 4, 5, 6 as a set of all the possible choices, comma 3. So in general, okay, when ordering is not important in a lotto game, in general, when you have X as a set of all the possible choices, and W being the set of all the winning numbers, the probability of winning the jackpot in this case is just going to be the ratio between these two. So we are looking at the cardinality of the permutations representing different ways of arranging the winning numbers divided by all the permutations of picking just n balls out of X. And that whole thing, when you get all the way to the end, becomes 1 divided by bar X bar, which is the number of elements in X, choose n. Are there any questions about this part? Questions? Yep, go ahead.
Is that the same as a combination?
Yes, because it's now combination. In other words, one way to look at combination is look at everything as permutation, except certain ways of arranging things is considered the same. So you have to divide it by how many ways can you arrange it, because there are quote unquote duplicates. So you have to count. Okay, so how many duplicates are we talking about? And the ratio between all the possible permutations and all the permutations that are considered duplicates of each other of what you're interested in, that ratio becomes the combination. So that's one way to look at combination, is really a ratio of permutations. All right, so are we okay with this, or? Yep, go ahead.
What was W again?
W is the set of winning numbers, as opposed to, so W is the set of winning numbers, and X is the set of all the possible numbers. So when you look at regular lotto, X is going to go from 1 to 47, and then the cardinality of W is going to be 5, because in super lotto, you are, to win the jackpot, you have to get all 5 winning numbers right. So W has a cardinality of 5. So in this case, I'm not even interested in the actual set W or the actual set of X. I'm just looking at the cardinality of those two. Okay. Any questions about this? No questions? All right. Now, when we study combinations and permutations, it is kind of important, because when you think about certain problems, okay, you're dealing with all the possible permutations, and there's a huge number. Okay, have I used the UPS truck example in this class? Finding the shortest route to visit all the drop-off points. Yes, I think so too. Yeah. So once you have a problem where you can say, okay, we have to explore n factorial, n being the size of the problem, and n factorial possible ways of arranging things, you have a really tough problem. That's really, really a hard problem. Okay. But our focus, is not even the time complexity of algorithm at this point, so I'm going to leave that topic alone for now. Okay, so we're going to get back to recursion, which is where the practice exam of number 2 is located. There are 2 of those. So I will start with spring 2016, because that's the one that is closer to us, and I taught the class a little bit better last semester as opposed to the previous semester to that. I would like to go through this, because this is going to be pretty much the same thing you have to read in your own exam, so it doesn't hurt to have this introduced first. So once again, I want you to write down your last name first, and then your first name, and then your student ID. The time obviously is not going to be the same, the date is not going to be the same, but it is still open book and open notes, just no electronics. I do not believe you will need a calculator, because you can leave the answers as formulas or formulae. So if you say, okay, the answer to this question is 1 over 16, choose 5. Okay, just leave it the way it is. Okay, because I don't really care about the actual value. It is how you get to the answer that is the most important part. It is an individual assessment, which means the score should reflect the competency of you and you alone. The answer should be independently and originally derived during the test. No sharing of open notes or books during the exam, and do not discuss the question with students who may not have taken the exam or during the exam. Use additional sheets of paper. So this is kind of important. If you think that you might need some additional sheets of paper, just bring 2 or 3 with you, just in case you need some additional room to write your answer. Write legibly. I cannot give points to answers that I cannot interpret without post-examination explanation, because sometimes people come back to me and say, "Oh, Tag, I really meant that over here with some scribble." Okay, so I cannot do that. Okay, if I cannot read what it is, when I grade it, I cannot ask the person to clarify later on. In the previous exam, all questions have equal weight, and there are only 4 questions. There were only 4 questions, and this exam accounts for 20% of your final grade, which is still true. Okay, second exam is 20% of your final grade. All right, so we can actually get to the questions now. Question number 1 is saying, okay, via lab testing, it is known that a particular data transmission mechanism has a certain error rate. When a 1 is transmitted, so a value of 1 is intended to be transmitted from one side to the other side, there's a chance of 2%. There's a 2% chance that it may be received as a 0, as an error, and 98% that it will receive properly as a 1. Is that okay? So if you want a mental picture of this, you can just kind of draw, well, I cannot find any dry board marker in this room. Oh, okay. Let me see if I can do it like this. I'll give it a shot. Which one should I use? Inkscape can probably do it. Let me see if I have another program installed here that can do a better job than this. And it's called Zernal. There we go. There we go. Okay, so this is my virtual notepad. So I can just draw a picture here. So this means that you're trying to transmit a 1. So the 1 is actually leaving the transmitter. But when you get received by the receiver, there are 2 ways to proceed because of errors. So when it is received on the other side, sometimes it is received, most of the time it is received as a 1. Okay? And you have a 98% chance that it is received as a 1. But there's a 2% chance that it will be received as a 0 because of transmission error. Okay, somebody turned on the microwave oven, and you get an error. Okay, so the chances in this case is, okay, if I use a text tool here, okay, this one is 98% of the time, and this one is 2% of the time. Are there any questions about this particular picture? On the left is representing what is transmitted, what is coming out of the transmitter. On the right is what is actually received by the receiver. And the error is just due to all kinds of stuff, atmospheric, disturbance, somebody turned on the microwave oven, can be just electronic issues on the receiver side. We don't know, okay? It's just 98% is right and 2% is wrong. Okay. So with the second problem, okay, let me see if I can change the font size, so we can either change the font size or I can zoom in. I think zooming in is probably the easier one. Okay, zoom in a little bit more. There we go. Okay. Okay, so this is for when you're transmitting a 1. When you're transmitting a 0, okay, it is a little bit different. So when a 0 is transmitted, then the chances of receiving it correctly as a 0 is a certain percentage, and the chances of receiving as a 1 is another number. So I'm going to draw the arrow here and draw the arrow here. So according to the question, when 0 is transmitted, there's a 4% chance that it is received as a 1 and a 96% chance that it is received correctly. So to document it over here, we basically say that there's a 96% it is received correctly as a 0, and there's a 4% chance that it is received incorrectly as a 1. So this is the kind of picture that we have, in this particular problem. Are there any questions about the assumptions, or how the probabilities are distributed? No questions? Okay. So now the question is asking, if a 4-bit pattern, the 4-bit pattern is being transmitted is 1, 0, 0, 1. When this particular pattern is transmitted, assume the transmission of a bit does not affect the error probability of any other bits. In other words, they are fully independent. Okay, transmitting 2 zeros in a series does not increase the chances or decrease the chances of the error rate that is already stated here. We want to analyze the overall error rate, and in the following space, create a table so that each row represents a data pattern that can be received, and on each row use a formula to express the probability of that data pattern being received. So tell me the chances of that particular pattern getting received. There's no need to work out the exact numerical value, which means you don't need a calculator. You just need to state how it is calculated. You can also use variables to reuse the same formula on multiple rows. Wink, wink, which means that can help save you time. Note that the summation of probabilities of each row should add up to exactly 1. In other words, when you add up all the rows, all the probabilities, they should end up as 1 because that accounts for all the possibilities. Okay, so let's go ahead and use a spreadsheet this time to represent the answer. Okay, so because a spreadsheet allows me to do calculations for one thing, and it is by default a table, so that makes it a little bit easier to deal with this stuff. Okay, so each row is representing a particular pattern. Okay, so I would use one column to just indicate, okay, what pattern are we talking about here? So what do you think are the patterns that can be received on the other side? I'm transmitting zeros and ones, okay? So, and there are 4 bits. So what are the possible patterns that can be received on the other side? Okay, 0, 0, 0 first, right? Okay, it all depends on how you want to do things. Okay, I personally like to do it like just adding 1 to a binary number. So this is just a sequence of values, represented as binary numbers. 0, 1, 0, 1. Come on. 0, 1, 1, 0. 1, 1, 1. 1, 0, 0, 0. 1, 0, 0, 1. 1, 0, 1, 0. 1, 1, whoops, 0, 1, 1. 1, 1, 0, 0. 1, 1, 0, 1. 1, 1, 1, 0. And finally 1, 1, 1, 1. So there are 16 of them. Okay. Why do you think there are exactly 16 of these patterns? Because it's 2 to the power of 4. Because we have each bit can have 2 configurations. It can be a 0 or 1. And we have 4 of those. So we have 2 times 2 times 2 times 2 as a total number of patterns. Okay, so these are the patterns that we are dealing with. So now we have to look at the chances of receiving that particular pattern. Okay, so with this one, okay, remember 1001 was the intended transmission. In other words, the first bit, okay, so this is first bit, I'll call it bit 0. Bit 1, bit 2, and bit 3. So these are the 4 bits. It doesn't really matter whether you count from left to right or right to left, because 1001 is symmetric. Doesn't matter which way you read. So in this case, a 1 is transmitted as bit 0, but it's received as a 0. So what are the chances that would happen? Okay, a 1 is transmitted, but it's received as a 0. So you go back to the assumptions here. A 1 is transmitted, but it is received as a 0. So you have a 2% chance here. So you say 2%, okay? And for the next bit, a 0 was transmitted and it is received as a 0. What are the chances that a 0 is received correctly? It's 96%. Okay. And the same thing applies to this one. It's 96%. And then for the last one, it is also 2% because of 1 was transmitted, but it's received as a 0. Is that okay? So you just work out this table, okay? I'm going to pick I'll pick this one as the next one to work on because it's really time consuming to work out the entire thing. So with this one, it is a 2% for the first bit because I'm looking at the most significant bit as the first bit. The second bit is still the same. And then the third bit is different because in this case, it was received as a 1, but it was transmitted as a 0. In other words, this would be the error chance of transmitting a 0. What percentage are we talking about? 4%, exactly. So we have a 4% here. And this one is also different because it was transmitted as a 1 and it was received as a 1 as well. What are the chances that the 1 is transmitted correctly? It's 98%. Okay. So that's basically what we are talking about here. And if you want to, you can just say that this is a product of the previous 4 columns. I mean, that would be sufficient. Is that okay?
I didn't understand that, Luis.
Sorry, yeah? Say
What
again?
did you mean by a product?
Product of these, okay? So if you really want to look at the value, this becomes the summation of, oops, not the summation, product of these numbers, which is going to be a pretty small number because the chances of having something that is transmitted incorrectly is pretty slim. Okay.
So we're calculating the chance that it is correct, or we're calculating the error here?
We are calculating the chances of actually receiving that particular count.
Okay.
So on one hand, 1001 was transmitted. On the other hand, I'm receiving 0000. So I want to know what are the chances that I will receive the pattern, which was supposed to be 1001 as 0000.
And then you said something needed to either sum to 1 or be a product?
Yes, the sum to 1 is basically when you sum up everything in column F, that should be a 1. Because that represents all the possible ways of getting things transmitted. Is that okay? So does anyone want to see this entire sheet worked out?
Is that what you're asking for in the question?
Yes.
Okay.
Well, what I'm really asking the question is just to confirm that you know how to work out the problem. In other words, you can say, P is 0.2, 0.02, and the Q is 0.04. You just work with P, 1 minus P, Q, and then 1 minus Q, and just populate this table with those terms. And then in column F, all you have to do is to say, okay, this is going to be the product of those 4 numbers on the same row. And that will be sufficient, because I don't need you to actually come up with the actual number. Yep.
Can you do an example with the variables?
With the variables?
Yeah, like P and Q like you were just talking about.
Yep, absolutely. So what you would need to do if you want to use the variables as names is you have to tell me the assumptions, because in the question itself I did not use any variables. So you can say P is 98% and Q is 96%. 96%. Oops. Okay, and you can even use other terms. Like you can say W is the other side of this one, and then X is the other side of this one. So now you can just say, okay, this is going to be a W, this is going to be a Q, and a W. So that saves you a lot of writing because you're just using these terms. And then there certain ones of these are symmetric. In other words, they give you exactly the same value. In other words, when you look at 0011, it has exactly the same chances as 1100 because the original pattern that was transmitted is also symmetric. So you can use a particular variable and just say it's the same as that one. So that's what I mean by you can use variables to help save you time, because there are many entries here that are exactly the same. Is that okay? All right, cool. Okay, so what I want to do is to work out the entire table using the exact values, because I do want to show you what the table looks like when we actually get to the value, which is something that you don't have to do in the exam. So I'm going to use an equation to find out what we're dealing with here. Okay, so let's see, what is the best way to do this? Okay, I can start with the if, okay? So I'm just evaluating whether I should use a string function to find out whether it's a 0, in the actual pattern, or whether I should use base conversion and then followed by bitwise AND in order to figure it. Well, actually, it's going to be division. I think a string function would work well in this case. So I need to look up the string functions. Insert function. And we are looking for a string function to extract just a portion of a string or text. It's called mid. Yep. Okay, they have mid. That's good. Okay. So now I can say if, okay, the test is mid this string. The start is going to be 1, and we are looking at one single character. So if this is a 0, it is incorrect. Okay, or I should say if it's a 1, it is correct. If it is correct, then we are going to say it's 98%. If it is incorrect, we will say it is 2%. And let's see if that works. Oh, okay, it doesn't like that. And it could be the use of single quote versus double quote. There we go. Yep, there we go. So, but with this one, I have to put a $ to A in order to reuse this, in the other ones. Okay. What was that? Okay, this is looking at the second one. Oops, I can't remember. So this is the second one. And then the chances are different this time. It's 96% and versus 4%. And also we are looking for a 0 in this case. A 0 is correct, so it's going to use the 96%. So this one is now done. And the other one is kind of the same, except we are looking at the third character. So I'll put a 3 here. Oops, it didn't accept that. 3, press the enter key. Yep, so it's a 3 here, and a 0 is correct. And then the last one should be the same as the first, except for which part of the string I should be looking at. So with this one, we are looking at the fourth character. It should be a 1. Okay, there we go. So now that I have the first row worked out, including this guy here, I can now just replicate it to the end, like so, and I have all the numbers. And you can see this cannot be right. Okay, so because this one should not be this high, and then 1001 should be the only one that has a high chance. So I got some of the things wrong. We can actually visually see that this column is incorrect. Nope, this one is incorrect. Because this is transmitted as a 1, but it is supposed to be a 0. It's received as a 1, I should say. It's received as a 1, but it was transmitted as a 0.
Then you put it as column 3. It says 3.
Yep, so when I made the correction, I did it incorrectly here. So we should say 2. There's a way to actually use the column number of the current cell as a part of the equation. I think it's just a row number or something like that. But we can. So now I just need to do this, fix that whole thing. So it looks right now, because the only one that has a high chance is the actual correct pattern. All of the other ones are, much lower. But you can also see, with this particular pattern, which is incorrect, is off by 1 bit. It has close to 4%, a close to 4% chance of receiving that particular pattern. So the 1, okay, is the summation of all of these guys. So when you look up all these numbers, the summation of all of those should add up to exactly 1. So we say the summation of all of these should be 1. There we go. Is that okay? All right. So once again, in the test, you don't have to work out the actual numbers because it takes a lot of time to write down these numbers. But you do have to tell me how you calculate these numbers. Okay? Is that okay? All right. So moving on to the next question. The next question is, function f is defined recursively as follows. F of 0 is 0 by definition. And then for everything that is greater than 1, okay, f of that number is f of x minus 1 plus 2x minus 1. Okay, so that's kind of the definition. Are there any questions about the definition itself? Let me just kind of zoom in so it's a little bit more readable, like that. Are there any questions about what f is or how f is defined? Z plus are all the positive integers. So if x is a positive integer which does not include 0, then we use the recursive definition. F of x is f of x minus 1 plus 2x minus 1. Is that part okay? All right. So my theorem is to say that for all x in Z, and then the superscript is an asterisk, which means we're looking at all integers, all non-negative integers starting with 0, f of x is actually x squared. That's the theorem, okay? And I want you to prove this using proof by induction. So how do you do this? Okay, you set up the base case first. Okay, so in this case, what would be the base case? 1. Base case is, no, it's not 1. It's even better. It's 0. You don't have to do a single calculation. The base case is f of 0 is 0. Okay? But that by itself is not a proof because we know this by definition f of 0 is 0. But what you need to do is to show that 0 squared is also 0 because you have to make a link between f of x and x squared. So you're basically just saying, okay, f of x equals to x squared is true when x is 0. But that's fairly easy to prove because one side is by definition, the other side is really just the square of 0, which is 0 itself. Is that okay? So if I were to do this proof, and I'm going to switch back to my Zerno screen, okay, which doesn't really work with the equations very well, but I think we can do this well enough. Okay, so we can say when x equals to 0 as a base case, the following is going to be true. F of 0, f of x is f of 0 because x is 0 itself, and that by definition is 0 by definition of f. And then on the other side, we can then say 0 squared, okay, I'm going to use this notation to mean 0 squared, okay, is, or I should say x squared. X squared first is 0 squared because x equals to 0, and that turns out to be 0. And as a result, f of x does equal to x squared when x equals to 0. Is that okay? Making the connection between f of x and x squared when x equals to 0. So the theorem is true when x equals to 0. We have our base case. So the next stage is to work on the induction step. Okay, so this is the induction step. The induction step always starts with an assumption. Okay, yep?
Did you not want to plug that into the other definition of the function?
The other definition, what do you mean by the other definition?
Was it f of x minus 1 equals...
Oh, we're going to do it here, yep. In the induction step, but not in the base case. Okay? So in the induction step, then we first make the assumption, okay? Assume f of x equals to x squared is true when x equals k. Okay? Need to prove f of x equals to x squared when x equals to k plus 1. That's the induction step, okay? So the assumption part is already given to you as an assumption. We just have to prove the other one. So what do we do here? And we have to say, okay, so let's check out what is f of k plus 1. F of k plus 1, by definition, is f of k plus 2k minus 1. Okay, this is by definition of f. Yep.
Wouldn't you want to prove x plus 1 squared?
Yes, but we'll get to that point. So I'm working out a very long, equality chain, so that by the end we should have k plus 1 and then the whole thing squared. That's what we have tried to work toward. Okay. Okay. So then what can we do about this? Now this is the most important part. Well, one of the most important parts of proof by induction is okay. So we are now expressing the bigger problem, the one that we are trying to solve right now, as a smaller problem, which is the one that we have already made the assumption about. So using the assumption of f of x is already x squared when x equals to x, we can now say that this whole thing is really k squared plus 2k minus 1. Is that right? Doesn't look right to me. I think I'm missing something. F of x is x squared. F of k plus 1 is f of k plus 2k minus 1. Oh, I missed one here. Because this number has to be the same as the number as a parameter. That's why it didn't work. Okay, so I'll keep it the way, and we'll keep it like this. So I messed up a little bit earlier because I should have used k plus 1 as the quantity being doubled. Is that okay?
And the one of the k squared is the k plus 1 minus 1.
Say again? Oh yeah, because once you expand it, right? Okay, so then we go ahead and expand. What is 2k plus 1? 2 times the entire thing, 2k plus 1. So this is 2k plus 2, and then we have a minus 1 at the end. Then you go like, okay, we can combine, we can collapse all the constants. So we have 2 minus 1 here, which is just boiling down to a single one. And from quadratic equations, you recognize this one as k plus 1, the whole thing squared. And as a result, we're done. Who knew that the squares of a integer can be defined in a recursive way? But it only works when it's an integer, okay? So it doesn't work with real numbers. Any questions about this? Yep, go ahead.
So you're not adding the 1 to the x, you're adding it only to the k.
Okay, so this part here, this is the actual theorem, right? So we have to say the theorem is true, but for which value of x? That's what it is.
Okay.
Okay. So are there any questions about this particular question? Now, in the exam, okay, when I ask you to prove a particular theorem and I indicate that you have to do it by induction, then you have to use proof by induction. There may be some other ways to prove this theorem, but if you use any other way other than proof by induction, there won't be any points, okay? Because the whole point of the test or this particular question is to see whether you understand proof by induction. So when you do a proof by induction, and let's just say that you cannot do the algebra part, but you do understand the principle of proof by induction, there will be partial credit just by saying that, oh, this is the base case, okay? Just by saying there's a base case and this is the base case and this is what we need to prove, okay? This is what, oops, I don't think there's a way for me to, maybe there's a way. Let me give, nope, maybe that. Yep. So there is a base case, and the base case is to prove that f of x is x squared when x equals to 0, just to indicate that has partial credit already rewarded. Because it is indicated, it's telling me that you know a part of proof by induction as a proof technique. Okay? And just by telling me that there is a proof by induction or an induction step, and in the induction step, this is what we need to do, there's partial credit for that as well. Now, obviously, carrying out the actual proof to bring it all the way to the end will give you full credit. but there is partial credit just by indicating that you understand the steps and the structure of proof by induction. Okay, question? Yep.
Can we put x equals 1 instead of x equals 0? Do that way?
Then you have to prove f of 0 separately, because the definition of f does not really indicate that it is true that f of x equals to x squared, even when x equals to 0. So even though it's trivial, you still have to tell me that it's true. Because otherwise, then we have that one value left alone, and we don't know whether it is true or not when x does equal to 0. So as trivial as it is, you still have to show that it is true. So you might as well use it as a base case. Okay. Any questions? No questions? Okay, if there are no questions, we're going to move on to the next question, which is question 3. So when you do have an exam where all the questions carry equal weight, then what you need to do at the beginning of the exam is to take a quick glance of the questions and find out which one to you is the easiest. Okay, now that can be different for different people. Some people may look at question number 3 and look at, oh, I can deal with head, tails, and stuff like that. So those people may say, okay, I'm going to work on this one first. Some other people look at question number 2 and say, I'm really good with proofs. Okay, and this one seems like it's going to be short. I'm going to work with that one. So depending on what you feel is the easiest for you, get those done first. Okay, then you go pick up the second easiest question and so on. So this way, you get all the points that you can possibly get, the easy points first. It's an easy decision when they all carry equal weight. Okay, if I assign different weight to different questions, then you kind of have to evaluate how much time am I going to spend on this question and how many points am I getting in return. But if they all have equal weight, it's an easy one. You just pick the easiest one to start with. Okay, just a minor point of how to how to approach an exam. Okay, question number 3 is one thing that we have kind of talked about, but we actually finished talking about this particular one, but I'm just going to go through this again. Assuming a coin is fair, it is not loaded. So in a sequence of 4 tosses, okay, the chances of having tail head should be 0.5 to the power of 4, because you get a 0.5 chance of getting a tail, 0.5 of a chance of getting a head, 0.5 of getting a tail again, and 0.5 of getting a head again. So the probability of getting a sequence exactly like that, tail, head, is going to be exactly 0.5 to the power of 4, because the coin is fair, it is not loaded. So at a casino, a coin is claimed to be fair. The casino claimed that the coin is fair, and you as an observer is observing these sequences. Okay, so you say, okay, 1, 2, 3, 4 coins, 4 tosses. Let me see what is the actual outcome. So we did some counting. So when you do all the counting, you found out that for all the sequences, okay, that ends up with 1 head and 3 tails, not necessarily having the head first and then 3 tails. It can be tail, head, tail, tail. It can be tail, 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 head. It can be tail, tail, head, tail. Okay, but when you count up all the sequences that ends up with 1 head and 3 tails, you count exactly 78 occurrences of that. Is that okay? And then you also did counting for results of 2 heads and 2 tails. Okay, so out of a sequence of 4 tosses, you add up. Okay, there are 2 heads and exactly 2 tails, and there are 146 sequences, each one being a sequence of 4 tosses that ends up in that configuration. Well, then what about having 0 head and 4 tails? Well, you do not count. Okay, what about 4 heads, 3 heads and 1 tail? Well, we didn't count that either. Okay, so you only managed to count these 2 specific configuration. Are we doing okay so far? Okay. So now the question is, how would you check whether the coin is loaded or not? Okay, what kind of math are you going to say? Okay, I'm going to compare. I will be comparing this versus that, and depending on whether it's the same or one side is greater than the other side, I can now start to suspect the coin is not loaded. It's actually loaded and it's not fair. Okay, so use the equations. Okay, you give me some formulae. You don't necessarily need to use numerical values, okay, because it takes calculations and you do not need to have a calculator in this test. Just tell me the conditions, which usually ends up as conditions. Yep.
So what you did, I remember you did this, pretty much this exact same problem in the notes about when you were doing when you said like when you're checking whether a coin was loaded or not, you did like the probability of getting heads, and you compared it with like, or you said like if there was like you get like 60 heads out of 100 coin flips, and then you did one other one where you got like 3 heads out of 5 coin flips, and you compared like the probability of that. I remember you did in the so wouldn't this problem be pretty similar to this?
Well, this problem is about ratio, okay, because it's based on what the ratio should be when the coin is fair versus the ratio of what you are observing.
Yeah.
Yep. So that's basically how you do this particular question. So let me see if I can, because in this case we have to use a bunch of equations. So let me check out how we should do this. Yep.
You could write down, first of all, like the probability of seeing 2 heads and 2 tails is going to be 4 choose 2 times p squared, where p is the probability of heads, times q squared. The probability of seeing seeing 1 head and 3 tails is going to be 4 choose 1 times p the first times q cubed. Then we get a ratio of p over q, and and that should be equal to 1.
Yeah, I'm more concerned about really just being able to display the equations in a mathematical format.
Use the curly brace for /choose.
I think this will work really well. Okay, so let's give this a try and see if it works. So we'll go ahead and so I'm going to do this EQN array. Okay, so what we're dealing with here, so let's say we have a chance of P being the chances of a head and Q as a chance of being a tail. Okay, so P is head, Q is tail. Okay, so now we're dealing with 4 tosses, right? So for each toss, the probability is distributed between P and Q, just like that. P plus Q should be 1. Is that okay? Because P is representing the chances of landing on a head, Q is representing the chances of landing on the tail. So P plus Q should be 1 because those are the only possibilities you can get when you toss a coin. Is that okay? So because we have 4 tosses, that means we are looking at this. We are looking at P plus Q to the power of 4 to represent 4 tosses, a sequence of 4 coin tosses. Is that okay? All right. So this seems really pointless because P plus Q is exactly 1, right? 1 to the power of 4 is 1. So what is the whole point of trying to look at this thing here? Well, the reason why we're looking at this is we want to look at this as a summation. Okay, so we are talking about a summation of I going from 0 to 4. Okay, oops. 0 and then caret 4. There we go. Oh, I see why it's having a problem. I need nesting here. There we go. Okay, so we're looking at a summation, and the term of each summation, I'm going to use a question mark here first. Okay, but each one is going to be it's going to have some power of P combined with some power of Q. Okay, so we're looking at P to the power of I, okay, times Q to the power of, in this case, 4 minus I, like so. Does this look vaguely familiar to you? because we talked about a much more general case when we instead of using 4, we use n. Does it kind of remind you of something that we have talked about? So we are really just looking at the coefficient here. The question mark is the coefficient of the term that has p to the power of I, q to the power of 4 minus I, and I can go from 0 to 4. Is that okay? Sorry?
The binomial.
Yeah, it's the binomial theorem. Okay, it's the binomial theorem. So by the binomial theorem, we know this question mark is a number that we are very familiar with at this point. Okay, so what should be this term here? No.
Or choose I.
There we go. Okay, does this look familiar? Even though in the text, when we did talk about this, we were using 1 plus x to the power of 4, or to the power of n. Well, we just use p as 1, and then q as x, and then we end up with this term here. Is that okay? So, what that means is, when you look at this whole thing, okay, you expand this whole thing, okay, if you really expand the entire thing, then the first term is just having q to the power of 4 itself, because 4 choose 0 is 1. Is 4. Okay, how do we know 4 choose 0 is 1? You can approach it by 2 different ways. One is to look at the meaning of choosing. How many ways can I choose nothing out of 4? There's only one way, because you end up with nothing, right? And then the next one deals with the case when I equals to 1. Okay, when I equals to 1, we're dealing with 4 choose 1. How many ways can I choose one thing out of 4? Exactly, there are only 4 ways, right? So we have 4 times, in this case, there's 1p, and then q to the power of 3 in this case. I'm just spelling out the individual terms, okay? And then the next one is p squared, q squared. How many ways can we do this? 4 choose 2. So now I'm choosing 2 things out of 4. How many ways can I choose 2 out of 4? Now this is combination, not permutation. So what is the definition of choosing? 4 factorial divided by 2 factorial times 4 minus 2 factorial, which is also 2 factorial. So we're dealing with 4 factorial divided by 4. 4 factorial is 4 times 3 times 2 times 1, which is 24. 24 divided by 4 is 6. There we go. So now we have 6p squared, q squared. And then the other side is symmetric. Okay, so we have 4p cubed q plus exactly 1p squared, or p to the power of 4 in this case. Are we still doing okay with this? Okay, so in class we talked about the binomial theorem, which deals with the first part, which explains all the different terms. In this case, I spelled it out completely. Okay, yep, okay.
Did you want us to show the sigma notation, or could we just skip to the?
Oh, you can skip to the coefficients.
Okay.
But I'm explaining the answer, so I'm going the whole way to explain it. Okay. So getting back to the problem that we have at hand, okay, we're dealing with a coin toss, problem, okay. So if I just switch back to the question itself, okay, so bear with me, switching between these two. We are dealing with 79 observations of 1 head, 3 tails, and we're dealing with 146 observations of 2 head and 2 tails, okay. So we're dealing with a ratio here. The 79 is corresponding to, oops, wrong tab. So the 79 is corresponding to 1 head, 3 tails, which is basically the 4 here. And then, oops, I keep using alt tab when I should be using just switching the tab here. And then the 146 is corresponding to what? The 6, exactly. So we're dealing with the coefficients. So we are now saying that 4 is corresponding to 79, and then 6 is corresponding to 146, right? Yep.
Can you explain that again? I missed it. Why are those corresponding to the 4 coefficient, the 6 coefficient?
Because this is telling you, what is the expected frequency of observing, in this case,
Oh, I see.
one head and 3 tails. And this is telling you the expected frequency of observing.
Two heads, 2 tails.
Yes.
Okay. Yeah.
Is that okay? All right. Let's do a sanity check here, okay? Because I'm looking at this, we're like, well, does it make sense to me? In other words, when you're tossing a coin 4 times, what is the combined frequency of all of these things? Okay. For each toss, we have 2 possibilities, right? Head or tail. And I'm tossing the coin exactly 4 times, which means I have how many possibilities? How many ways can the outcomes come out? Head, tail, 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 head, tail, head, 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 tail, and so on. So how many possible ways can I arrange things? Total. 16. Okay, 16. So when we add up the frequencies of each one, are they adding up to 16? There's one observation that should be all tails, one observation where they should be all heads, 4 observations that would have 1 head and 3 tails, 4 observations where we have 3 heads and 1 tail, and 6 observations where there should be 2 heads and 2 tails. Remember, the ordering is not important, we're just counting. Do they add up to 16? They do. Okay, so it passes the sanity check. Okay, so every step along the way, I'm just double checking. Okay, is this right? Does it feel right to me? Okay, very good. So now, having this, we can now say, okay, so the next thing we need to know is to say that the ratio of 4 to 6, okay, should be about the same. Okay, so I put a question mark here. Is it about the same as 79 to, what was that again, 146? Okay, that becomes the question, and that is part A. Part A is really just asking, okay, I know that the ratio of the observations of 1 head and 3 tails and 2 heads and 2 tails should be somewhere around 4 to 6. The observed ratio is 79 to 146. So now the question is, if the coin is fair, I should be seeing about the same ratio. If this is off by a lot, then there's a good chance that the coin is loaded. Is that okay? That's part A of the question. It's really just to show the 2 ratios and ask the question, are they close enough? You don't have to say exactly how close they have to be. You just have to say these 2 should be about the same. That's all I'm looking for. Okay? All right? All right. So now we go back to the question. Go to part B. Part B is if you figure out how to check whether the coin is loaded by comparing the 2 ratios and see how close they are, also indicate how you figure out how the coin is loaded. So if your conclusion is well, these 2 numbers are kind of different, so I'm suspecting the coin is loaded. So how do you figure out how the coin itself is loaded? That becomes the next question. So getting back to the equation, how do you resolve that? Yep.
You can figure out what P over, you use that to figure out what P over Q is, and then you effectively get the odds of the coin. Well, modulo some probability distribution, and then if that ratio of P over Q is close enough to 1, then that'll tell you how much the coin is loaded by. Like if it's like 2 to 3 or something like that, then you can pretty much say, okay, with high probability the coin is loaded. If you want to do it properly, what you really have to do is define a probability distribution, a prior probability distribution on P, but if you just want to eyeball it, you can just kind of take the ratio.
Okay, so what we have here is this part here, Okay, this actual, not just the 4, okay? When you look at 4 times PQ cubed, and that number versus 6 times P squared Q squared, that ratio is exactly 79 to 146. Okay, let me just state that one more time. Okay, so I'll make sure that this is clear. Okay, 4 to 6. What it should be when P and Q are the same. That doesn't show very well, does it? Well, it's actually just over here. Okay, well, if it doesn't do well with this one, I have to find out how to do this. Let me see if I can do this. Just text. Okay, closer, right? Yep. Well, all the spaces combined into one, so I can't really. And it's still trying to do the centering of the other part because of the earlier, formatting. Let's see. Let me see if I can do this. Yep, I can do that. Okay, so that will certainly help with this. So cut, paste, like that. Much better. Okay, excellent. Okay, so 4 to 6 is what it should be when P and Q are the same. Because when P and Q are the same, P times Q to the cube, P cubed, should be the same as exactly the same as P squared Q squared, because they're all 0.5. Does that make any sense? So when you look at 4P cubed, it should be the actual ratio. When you look at 4P, it's better to write it down because it's harder to say it. Okay, so 4PQ cubed to 6P squared Q, P squared Q squared. Okay, so is that good? When P and Q are the same, when you look at the ratio 4 versus 6, should be the same thing, at exactly the same thing as 4 times P times Q cubed versus to the ratio of 6 times P squared and Q squared. Does that make any sense? Because when the coin is not loaded and it's fair, P is 0.5, Q is 0.5, right?
Yeah.
When they're the same, then P times Q cubed versus P times P squared, Q squared, they're exactly the same number. They're all 0.5 to the power of 4. That's what happens when the coin is not loaded. But what are we actually observing? We're observing this ratio not matching 4 to 6. What we're observing is this ratio is 79 to 146. That's what we're observing. Okay? So getting back here, I am going to write this, okay, and say, okay, so 79 to 146 is what we actually observed. Is that part okay? So now we have a discrepancy because 79 to 146 is not exactly that close to 4 to 6. Are we? Yep, go ahead.
What did you mean when you said in the second line there, same as the ratio on top?
This ratio, if the coin is fair, 4 to 6 or 2 to 3 if you prefer, should be the same ratio as this one.
Okay.
But that's not what we're observing, okay? So what we are really observing is 79 to 146. But what that really means is this number turns out to be 79. This number turns out to be 146. Is that okay? Okay. So now we can actually get to the crux of the whole thing. Okay. Because what we are observing here, to resolve what is actually P, how the coin is loaded, we're looking at something like this. Okay, so we're looking at so just bear with me, because when you look at this part here, it's going to look pretty bad, because I need to finish the formatting so that it makes sense. Okay, so we are looking at the ratio of 79. Okay, and the problem of it's rolling around is not helping either. Okay, divided by let's say 4p cubed, q cubed. Okay, cubed is to the power of 3. There we go. And then on the other side we have 146. Oops, 146 divided by 6p squared, q squared. There we go. Okay. Is that okay? So if you want to say that a coin is not loaded, and the observation that we make is representative of the actual behavior of the coin, then we can establish this equality. The chances, the relative chances of observing a sequence where you have 1 head and 3 tails, we are using 79 to correspond to that, because that's actually what we observe. And then the chances of observing exactly 2 heads and 2 tails, but in any order, what we are observing is we have 146 of those. So I don't even really know as a total how many observations I have done, but just by using the ratio of the observations of these 2 particular type of sequences tells me that this equality should hold. Are we still doing okay so far? It's because this is the actual probability. Okay, let me see if I can highlight just that part. This part here, the 4pq cubed, is representing the actual probability of observing 1 head and 3 tails in any order. We ended up observing 79 of those. The other one, which is 4 times p squared times q squared, is the actual probability of ending up with 2 heads and 2 tails in any particular order. We ended up observing 146 of those. So based on what we observed, which is 79 and 146, those should correspond to the respective probabilities. So we are now trying to resolve what is P and what is Q. Yep?
So you're dividing the observances by the
probability of those observations. Yep. Okay, so now we have 2 unknowns, quote unquote, 2 unknowns and 1 equation. How do we resolve 2 unknowns with 1 equation? Well, you cannot. But we really only have 1 single unknown. What is the relationship between P and Q?
Equal to 1.
The sum should equal to 1. P plus Q is 1, which means 1 is 1 minus the other one. P is 1 minus Q, or you can say Q is 1 minus P. So now we can actually resolve it. I mean, all you have to do in this particular question is to get to that point and just basically say that copy, paste, and doesn't, okay. I'm just, 1 minus P, 1 minus P, and then the other one is that as well. We have 1 minus P. There we go. I'm just going to scroll down here just so that you can see the actual end result. So because I know the relationship between P and Q, the P plus Q is 1, right? So that makes Q equal to 1 minus P. And I just plug in those 2 over here. You don't need to resolve this. Okay, I'm not asking you to solve for the actual P. I'm just saying that, okay, if you can tell me this equation, I'm good. Okay, perfect score. Is that making any sense? Yep.
I understand everything except for why those ratios should equal, why the equality stands.
Why the equality stands? In other words, why we have this equality.
Yes.
This one here. It is because when you look at the expanded form of P plus Q to the power of 4, okay, what is each term representing? q to the power of 4 is expressing the probability of observing 4 tails out of a sequence of 4 tosses. The next one, 4 times p q cubed, is representing the chances or the probability of observing 1 head, 3 tails in any order. The next one, 6 times p squared, q squared, is representing the probability of observing 2 heads and 2 tails in any particular order. Is that okay? So if we actually ended up observing 79, and this is the probability of observing 1 head and 3 tails, this ratio, not ratio, but this number, 79 divided by the probability of observing that, is actually telling you how many observations we probably have done as a total. Okay? And then the total number of observations should be the same on the other side. So that's why I can put an equation, an equality here. Okay? Because one is the frequency of actual observation, and then the bottom part is the probability of making that observation. Is that okay or not? So once you figure out p, because now it's solvable. I know this looks kind of ugly, but it is solvable. Okay, because now we have just move all the terms up, so you don't have any division. Then you can solve it. I mean, you can use a calculator to solve it. You can use a spreadsheet to do it. You can just approximate the answer. But p is now resolvable. And you don't have to resolve it. You just have to show me the equation to the point where it is resolvable. Resolvable. Yep.
Wouldn't it be the other way around?
Say again?
Wouldn't it be the other way around? Wouldn't we have for PQ to the third divided by 79? Wouldn't that make for our total observances?
No, because that would be a very small number. This is a small number to begin with. P is less than 1, right? 1 minus p is also less than 1. So you're looking at a number that's less than 1 times the cube of another number that is also less than 1. So that makes it a pretty small number.
So are we going to end up with something less than 1?
You mean 79 divided by this?
No.
Or do you mean p?
In the denominator.
In the denominator. It is definitely a very small number. What is the largest number you can end up with as the denominator? How do you maximize, p times 1 minus p cubed?
If they're both 0.5?
When they're both 0.5, very good. So when they're both 0.5, what is the entire denominator? 4 times 0.5 to the power of 4, right?
71.
No. You're talking about 1/16 times 4, so that will make it 1/4. 0.25. So the largest value you can have here is actually just 0.25. And that's when the coin is not loaded. As soon as the coin is loaded, it's going to be smaller. So we are dealing with a large number here. This number is the estimate of how many observations we have done actually at the casino.
Okay, now that makes sense.
Okay. So that answers the other part of the question. So part C is really the same as part 2. Assuming the observation is representative of I actually answered part C already. Assuming the observation is representative of the nature of the coin, present equations. That one last equation is the one that we need to use to solve the actual probabilities of a head versus a tail outcome after a single toss. There's no need to resolve the actual values, but the equation should supply enough information to solve for the values. And in this case, I specifically say use x to express the probability of a head, which is p in our equations. This part may reuse or repeat parts of the other 2 parts. So you can just say, refer to part 2, we have this equation already, and we're done. Is that okay? For number 3. And then we go to number 4. I mean, do you guys see actual, applications of this stuff? I mean, if you go to the casino and you make some observations, and then you can say, hey, out of Okay, what we have not talked about is the large number theory, okay, which is basically saying if you observe a huge number of something, the observation should get pretty close to the nature of the thing. The casino cannot deny and say, okay, you have only made 10,000 observations. Your observations cannot be representative of the coin. That will not hold in the court.
You would get kicked out though. Like
Huh?
if you sat there making observations, you would get kicked out. Maybe if you were playing D&D with your friend and you weren't sure if they were using a fair dice or something.
I think if you make observations of just counting the heads and the tails, it's different from counting cards.
No, they can choose to kick you out.
Or they can always choose to kick someone
They're not
out
gonna-
just
if
because
you got
I
like a
don't.
notepad and you're like doing stuff.
Nah, you use a little Bluetooth device in your pocket. You just click one button when there's a 0, and click when there's a head, and click the other button when you have a tail. So it just
But Crack didn't know anything about that. But you would not know anything about that.
So because I think but you're right. They can kick you out for whatever reason they want to use to kick you out out of a casino. Especially when you try to find out whether they are cheating or not. Yep.
I had kind of for the last one, and I don't know if this is a quick answer or not, but what if, how would we modify that equation if it wasn't binary, like it wasn't heads and tails, like let's say there's 3 possible outcomes.
Then you cannot use the binomial theorem in that case. Like tossing a dice, right? So that's a little bit more. That's difficult. Yeah, that's different.
Okay.
Yep. Okay. Question number 4 is the last one. It is requiring you to use proof by contradiction that this particular algorithm is correct. Okay. I'm not asking you to prove that it will exit. I'm assuming that this will exit already. I'm just saying that is the answer correct? When the algorithm says return I is less than n as an answer, is that really reflecting that we have found the value k in the array? Okay, that's what it's asking. And I want you to use proof by contradiction. So how do we use proof by contradiction? This one, I'm going to just verbally describe the answer because we are running out of time. Okay, how do we use proof by contradiction? What is the first step of proof by contradiction? You negate the theorem. Okay, very good. So what is our theorem in this case? The theorem is basically what I claim the function is going to do. This is the theorem. The function returns non-zero if and only if k matches the value of at least one element in the array A. That's the theorem. So the negation of that theorem is to say the function returns a non-zero. It does not return a non-zero if and only if k matches the value of at least one element. You just negate that. Okay? So which in return means that the algorithm may return the non-zero when there's no value in the array having the value of k. It may also return a0 when there is a value in the array matching the value of k. So both of those would be cases of the negation of the theorem. Is that okay? So you have to tell me why they're not possible, why those cases are not possible. So we'll take one at a time. We'll tackle one at a time.
We have to show both.
You have to show both, but you have to but you can only do it one at a time. So we'll pick the first one first, which is basically saying the algorithm returns non-zero even though nothing in the array matches the value that we are searching for. Is that okay? Case 1. So that basically means it's returning a non-zero, but the non-zero is because of this expression. I is less than n is true. Is that okay? When I is less than n is true, how did we get out of the loop? When you look at the structure of the loop, it requires I less than n to be true to stay in the loop, but there's one more condition that has to be true to stay in the loop. It's this one. Okay? A bracket I cannot be equal to k. So if I did get out of the algorithm, and I is still less than n when I got out, what has to be false? How did I get out of it?
confounded.
This algorithm is, this expression is false. But what does it mean when this expression is false? When it is false, that a bracket I does not equal to k, what does it mean? It means they are the same, right? If a bracket I does equal to k and I is less than n is representing the number of elements in the array, don't I have a problem? Because then it means it's bound. But I just said that, because I am taking the negation of the theorem, that in this case the function returns non-zero even though no element in the array matches the value k. I just have a contradiction. Okay? The conclusion of the logic contradicts the assumption in that particular step of proof by contradiction. Is that okay? So what about the other case? The other case is the algorithm returns a 0 even though something in the array does match the value of k. So how would you go about doing that? In other words, in this case, we are saying that this expression is a 0 even though something in the array does match the value of k. Okay, if this is 0, how did we get out of the loop? This is 0, so we got out of the loop because of that. Now this is also because in C and C++, when you have a conjunction, it is short-circuited. Okay, so I know for sure that when I is less than n is false, by the time I got out of the loop, it is false here as well. Okay, but why would that be a problem? When I is less than n is false, it means that I is greater than or equal to n. Okay? I started off with a value of 0. How can it possibly be greater than or equal to n? We have to go through this n times. That's the only way, right? As we go through this n times, we are also going through this n times. Right? When we go through this part n times, a bracket I does not equal to k, and I got the value of 0 all the way up to n minus 1, that means we have done this comparison exactly n times, and every single time it is returning what? True or false. Remember, we got out of the loop because of this condition failing, not because of this condition failing. So this condition stayed true the entire time. When I was equal to 0, all the way when I equals to n minus 1. In other words, we examined every single element in the array, and every single time this statement is true, which means we haven't found the element in the array. But that contradicts with the assumption that the array does contain the element that we're looking for, and yet the function is still returning false. So now we have dealt with the two cases of proof by contradiction, because those two cases combined is the negation of the theorem. So by combining those two particular cases, we have just proven the algorithm is correct, because it is not possible to be wrong. Is that okay? Okay. So I'll go ahead and write this down, in the document, so that we have a version of the written part, because I cannot write it down because we're already out of time today. All right. So rest well. Get your notes ready, and just prepare for the exam on Monday. Sorry?
Don't forget to upload a video.
Yep. I will do that.
Just making